In this video, we solve problem 14.3.023 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. So we're given this double integral in rectangular coordinates, and we're asked to evaluate the iterated integral by converting to polar coordinates. And they give us this answer box. So they're looking for r to go from 0 to some function of theta, and theta to go from theta equals 0 to theta equals some other number. They're looking for the correct integrand. And they also ask for the answer. So this is what you'll see if you're solving this problem in WebAssign. And this is important because there is more than one way, to represent a region in polar coordinates. So they give us this. They tell us that theta has to go from 0 to some number. We have to keep that in mind when we're coming up with the appropriate bounds for this double integral. Okay, so first of all, if I want to convert an integral to polar coordinates, I need to sketch the region of integration R. So remember, these bounds go with this variable, and these bounds go with this variable. The inside bounds go with the innermost variable, and the outside bounds go with the outermost variable. So this is telling me that y starts at 0 and goes to that square root. And x starts at 0 and goes to 8. And this actually represents 4 separate curves. So I've got y equals 0. Now remember, y equals 0 is the x-axis. A lot of people think it's the y-axis, but it's not. Y equals 1 is here, y equals 2 is here, y equals -1 is here, so y equals 0 is right there in the middle. That's one bound. X equals 0 is another bound. That's the y-axis. X equals -1 is here, x equals +1 is here, x equals 0 is right in the middle. Then we've got x equals 8. So that's another vertical line. And then the most interesting boundary that we're given is y equals this square root. So let's focus on that one. Basically what we want to do is we want to rearrange this so that it looks like one of the functions that we're comfortable graphing. Like, this doesn't look familiar. I don't remember learning in pre-calculus or college algebra how to graph the square root of a polynomial in x. But I do know that if I square both sides and I've got an x squared plus y squared in my equation, or an x squared minus y squared, it's probably one of our conic sections. So the first thing I would do is square both sides to get rid of that radical. And remember, your reasoning is you're trying to make it look like the equation of one of those graphs that you're comfortable with. The square root and the squaring function undo each other, so you have this. Now remember, y was the positive square root, so you should state for yourself that if y is a positive square root, it has to be positive except for when it's 0. So this is true, but we want y to stay non-negative. And then we've got an x squared term here and an x term here, so we'll add this to both sides or subtract that 8x from both sides. Sort of moving it over to the left. And we see we've got a circle. Now it's not obvious that we have a circle yet, but I've got an x squared term, a couple of x squared terms, and a y squared term. So I think all I have to do is complete the square to write this as the equation of a circle. So this is the number in front of the x. That's what I call b. So many people call b. You want to take half of that and then square it. -4 times -4 is +16. So that's what we have to add to complete that square. And that's legal as long as we do it to both sides. Now this is a perfect square, so we want to write it as such. 4 times 4 is 16. -4 plus -4 is that -8. So we have this. Now remember, the center of a circle comes from taking the number you're subtracting from the x and the number you're subtracting from the y in that standard form. Whatever number you see there, it's going to have the opposite sign. So if you see a -4, the x-coordinate of the center is the +4. There's nothing being subtracted there, so that's a 0. And this number on the right-hand side is r squared. If r squared is 16, r is the square root of that, so r equals 4. So what we've got is a circle centered at x equals 4, y equals 0. So that's right here. And it has a radius of 4. Now don't forget this. That's our fourth curve there. We graphed y equals 0, x equals 0, x equals 8, and now we want to graph y equals this square root. Well, that square root is this. It's equivalent to this with y greater than or equal to 0. So I've got a circle centered at 4, 0, and the radius is 4. So we're going to go left 4 and right 4, up 4 and down 4 if we were graphing the entire circle, but y is greater than or equal to 0, so we're just going to get the top half. So that is our fourth boundary. And I think we can all see from that that the region bounded by this line, this line, this line, and this curve is this region right here. Okay. So that's the first thing. You always want to graph the region. And you're doing that by graphing the boundary curves. Okay, once you've graphed it, you want to describe the region in the new coordinate system in polar coordinates. Well, I think we can see then that if theta is starting at 0 and they're requiring us to start with theta equals 0, we start here at 0. Theta is going to start at 0 and it's going to sweep. Remember, it's an angle that sweeps around the xy plane. It starts at 0 and it sweeps up to here. I know it doesn't look like it's at pi/2 radians, but it's tangent to that y-axis. If we got really, really close, that's getting infinitely close to pi/2 radians. So we're going to go from 0 to pi/2. That's that right there. And the bounds for r come from the bounds for this semicircle. Now r equals 0 is right here. So r is going to go from 0 out to this curve. Now we just want an equation for that curve. Well, one way to find the equation for that curve is to start with this rectangular equation and convert it to polar coordinates. Or I think it might be easier to start with this equation and convert it to polar coordinates. Remember, these are all equivalent as long as y is greater than or equal to 0. So starting here is just as good as starting here. And I think starting here is preferable to starting there. So let's start right here. I'll rearrange it a little bit. I've got x squared plus y squared minus 8x equals 0. And I will add the 8x to both sides. And again, my reason for that is that I'm trying to make this look like some of the equations that I'm familiar with that allow us to convert from polar to rectangular and vice versa. So let's just write down some of those equations. Remember, when you're in polar coordinates, or when you're converting from rectangular to polar, x squared plus y squared equals r squared. We also know that x equals r cosine of theta and y equals r sine of theta. If you don't remember that, that's okay. We can look that up. can watch that video too to refresh our memories. But I'm taking this and I'm trying to make it look like this. That's why I grouped that x squared plus y squared together, because I knew if I did, I'd be able to replace it with r squared. And that 8x I moved to the other side because I wanted that r cosine of theta on this side. So now I'm going to substitute because my goal is to get rid of the x's and y's and go to r's and thetas. I've got r squared equals 8 times x, and x is r cosine of theta. Now, typically, I would not recommend dividing out the r, but that's legal in this case because the equation that results will still take care of r equals 0. So if we divide out r, we get r equals 8 times cosine of theta. And if you're saying to yourself, didn't you just omit the fact that r equals 0? Like, what if you accidentally divide by 0? You know, something like that. Those are all excellent questions. But let's think about it. R equals 0 is also a solution to this equation, because if theta equals pi over 2 or any odd multiple of pi over 2, we're going to get pi over 2 and 0, 3 pi over 2 and 0, 5 pi over 2 and 0. So r equals 0 is included as a solution of this equation. Okay, so that is one way to represent this curve. And that means our bounds for r start at 0 and go out to that curve. So r goes from there to there. And because of what we were talking about earlier, theta is an angle that sweeps. It sweeps from 0 to pi over 2. Okay. Okay, now remember, whenever you're switching from rectangular to polar coordinates, you need new bounds, and that's what we just did. The way you get the bounds is you graph the region and then you describe the region in polar coordinates. You may have to convert some equations from rectangular to polar coordinates just like we just did, and then look at the region and let the region tell you where theta starts and where theta stops and where r starts and where r stops. Okay, the next thing we need is an integrand. So we need to convert this xy into an appropriate function of r and theta. And basically the way we do that is we just use this again. So we need the new integrand. So you want the original integrand in terms of r and theta. I guess we're not finding it. We know where it is. I'm going to write the original integrand in terms of r and theta. So we're given xy, and x is r cosine theta, y is r sine theta. So you just substitute those in and simplify. You get r squared sine of theta cosine of theta. Okay. And the last piece, it's a very important piece, is that you need a new dA. In rectangular coordinates, dA is dx dy or dy dx, same thing, because multiplication is commutative. We can multiply in any order we want. But in polar coordinates, it turned out that dA was r times dr d theta. You need that extra r. Okay, so now you put all the pieces together, and that's going to give you your double integral. We've got our new bounds. Theta starts at 0 and goes to pi over 2. The constant bounds go on the outside. R goes from 0 to 8 cosine of theta. We need a new integrand. That's this guy right here, xy, in terms of r and theta. And then dA is r dr d theta, and I put that in the right order. I'm integrating with respect to r first because r depends on theta, and theta is going from a constant to a constant. Now this is our new integrand. So we took our old integrand and we multiplied it by r. Our old integrand in terms of r and theta multiplied by r is the new integrand. And of course you want to simplify that. That r squared times that r is going to give us an r cubed. we have r cubed sine of theta cosine of theta. Okay, great. Now we just need to evaluate the integral, and that's pretty simple. So I'm going to do that on the next page. All right, so we're integrating from 0 to pi over 2. We've got the integral from 0 to 8 cosine of theta, and our integrand was r cubed sine of theta cosine of theta, dr d theta. Start on the inside and work your way out. Sine of theta and cosine of theta are constant with respect to r, so you can just write those down, factor out that constant, and then anti-differentiate r cubed, excuse me, with respect to r. So we use the power rule. Add 1 to the exponent and divide by the new exponent. Then evaluate from r equals 0 to r equals 8 cosine of theta. And you subtract, of course, by the fundamental theorem. So we're going to have the integral from 0 to pi over 2 of this. When r gets replaced with 8 cosine of theta, we've got 8 cosine of theta raised to the 4th. And then we evaluate this at r equals 0, which is just going to give us 0. So we'll have all of this minus 0, which is just this, times d theta. Not bad. We just anti-differentiate with respect to r. Then we use the fundamental theorem. And now we've just got to do a little bit more algebra and then finish this. So we have 8 to the 4th. You can factor that out. And you're dividing by 4. We've got a sine of theta over here. And you've got 4 cosines times an extra cosine. So that's cosine of theta to the 5th. Oops. Now you could write that as cosine to the 5th of theta. That's the standard notation. But I really like this notation because this helps me see that it's going to be a u substitution to evaluate the integral. So we're just going to anti-differentiate with respect to theta, and we let this be our u. The derivative of cosine is negative sine. Don't forget your d theta when you're computing du. And I don't have a negative cosine, or I don't have a negative sign, so I will multiply both sides of this equation by negative 1, and I get negative du is a positive sine of theta d theta. So we're pretty good to go. I've got everything I need to rewrite this part in terms of u, and that's just a constant, so that's no problem. But we also need new bounds. Remember how the bounds work. You just take the old bounds, that pi over 2 and 0, and you substitute them into the equation to get the new bounds. So this was our upper limit. So new upper limit of integration, or upper bound of integration, comes from substituting the old upper limit of integration into the formula for u, that u value that we chose. Or I guess it's a u function that we chose. At pi over 2, a u is cosine of pi over 2, and cosine of pi over 2 is 0. Remember, cosine looks like this. All the interesting things happen at 1/4 of the period. It's 0 right there at pi over 2. And at 0, we've got cosine of 0, and cosine of 0 is 1. It's at the max there. So now we've got everything we need to rewrite all of this in terms of u. If you want, you could write that differently. It's 8 cubed times an extra 8, and 8 is 4 times 2. Why would I do that? It's because I wanted to reduce those 4s. Okay, now let's see what's left. This is my new upper limit, and this was my new lower limit. because I took my original lower limit, that's a lower limit for theta, and I substituted it to get a lower limit for u. So u goes from 0 to 1, or excuse me, 1 to 0. And then this is u to the 5th. And sine of theta d theta is a -1 times du. Now, if you don't like this going from 1 to 0, that's okay. You can flip it as long as you multiply the result by -1. So we end up with 8 cubed times 2. And then I can write that as the integral from 0 to 1 of positive u to the 5th du. I flip those and I multiply by -1 to get rid of that negative. Okay, so now we're here. I want to add 1 to the exponent, divide by the new exponent. 6 is 3 times 2. As my 2's reduce, and then I can evaluate from 0 to 1. So I get 8 cubed over 3 times 1 to the 6th minus 0 to the 6th, which is of course just 1 minus 0 times that number. And I don't know what 8 cubed is. 512. Oops, sorry for that reflection. So at 512 over 3. And if you're saying to yourself, what is that? Well, that's the value of this double integral in polar coordinates. 512 over 3, which is the same value as that double integral in rectangular coordinates. It's a double integral of xy over this region. Since that region's part of a circle, this is going to tend to be easier than that. Because, yeah. It just makes more sense to do this in polar coordinates because the region is part of a circle.